and I've tried out most things in basically complex dimension, and it's work perhaps the most useful thing you'll learn in this lecture is this following source. There's a book by Stephen Boyd and Vanderbilt. This book here, and that's the webpage. And the good news is that Stephen Boyd has an agreement with Cambridge University Press that this book will be available for free on the webpage for this entirety. It's extremely good. So this next lecture is based in part on that book. Another classics, and they get more and more practical as we go down this list. But this is highly recommended because it's pretty complete. Okay, we've already talked about complexity a bit, but let's just go over a few named sets. People give things names, usually means they think they're important, which is why every paper tries to name its algorithm with a nice name. So, what is an affine set? An affine set, the name for affine here, is just a combination of points, where the points are in Rn, such as these that sum to 1. They do not have to be positive, they can be anything. They can choose origin here to get a substance. Okay. The convex set is more restricted, C to convex. Again, it's a sum. Again, the x's are in Rn. And again, they sum to 1. Now these guys are positive. So the convex set, where 2x is then 1x cubed here, is the affine set defined by this sum here. The convex set is just a line from the one. There's also what's called a cone over cone, it's already C. So if x is in a cone, in a simple definition, and so is some scalar times x, where the scalar is positive, or 0. And since this can be 0, that means 0 vector must be in the cone. So here's a typical cone. I have some vector x. There, I extend it, that's also the cone. The cones need not be convex sets. Here's an example. I have vectors going this way, vectors going this way. This defines the cone, right? So just multiply it by theta. And then it's not a convex set, because I have to leave the set. If I draw a line between 2 points here, I have to leave the set. So a cone that's not your typical Rn, positive semi-definite matrices. Okay? You do this, you get a positive semi-definite matrix. That's a subset of the vector space of real matrices. So now, a bunch of vectors, n vectors, are called affinely independent. If you just take one of them, and then what you get, by subtracting that one out from the rest, are linearly independent. And in fact, in that next book, these are sometimes called invariant position, if that's the case. These x's. Another specially named set is simplex, an elemental simplex. It's just a set of convex combinations of a given set of affine independent vectors. Two vectors here. Here I've got 2 vectors that are affine independent. One is affine independent. This one is linear. So it's called the convex sum of these guys. So this is actually this is a regular because it has the same length size. It's easier and much more convenient for calculations to embed a regular simplex in this case R2 than R3, because then the edges of the simplex are just unit vectors, and they're all orthogonal. You can see why that would make calculating the simplex easier, regular simplexes. Here's a kind of amazing fact. For a regular n simplex, or simplex in n dimensions, the distance between any 2 vertices is always the same. If you have a 63 simplex, choose any 2 vertices, the distance is always square root of 2, which sort of gives you a feel for what happens in higher dimensions. Distances are everything particularly far from everything else. And our intuitions fail miserably, by the way. Okay, let's quickly go to complexity. So we've already done this, but this is just recap. The convex set is a subset of vector space, such as the 2 points unit, and so there's everything between them. So this is not a convex set. So an example of one convex set that's not an Rn is considered matrices. Both are reals. Sn, okay, so if I've got 2 matrices and the positive definite. Sorry, yes, then this storage is also positive vector. The theta between 0 and 1. Therefore, that's the convex set. So here's 3 equivalent definitions of convex function. So there's two ways in which convexity is used. It's used to define sets, and it's used to talk about functions. And for functions, there's two kinds of convexity. There's just convexity and strict convexity. Here's the three equivalent ways. So we have geometric interpretations. The first you've seen is just that the f here has to lie below the line joining 2 points x1 and x2. So there's geometric interpretation. This is strictly less than and it's strictly convex. Here is one that uses first derivative. And this just says that the function has to lie above every tangent. So you draw a tangent on the function must lie above that line. In fact, for a convex function, this blue region is called the epigraph, and that's the convex set. Here's another very useful one. The Hessian is positive semi-definite for all x in the domain of f. This is obviously an alternative to the domain of f. If that's true, then the function f is convex. But what about strict convexity? Is it true necessarily that if this is positive definite, then f is strictly convex? The answer is no. Watch out for that. It's certainly true by definition that it's strictly convex at this point, right? It's strictly below that line everywhere. It's strictly convex. Here's the theorem. If the domain of f is convex and the Hessian is positive definite, then f is strictly convex. But if f is strictly convex, this may not be positive definite. For example, x to the fourth is a convex function, but its Hessian vanishes in the origin. However, if f is quadratic, then it is equivalent. The positive definiteness of the Hessian is equivalent to f being strictly convex. And I've already talked about how every norm is convex. Here's a little puzzle for you. There's a one-line proof of the norm. Every norm is convex, no matter what the norm. Give me a norm H, see it, if you like. Are there any norms which are strictly convex? And you can answer that. Here's another one. These are all one-line positives, by the way. Take an arbitrary convex function, some arbitrary probability distribution, to the expectation of that function and that distribution. And it's always true that if f is convex, this is the faulty cause. So you can see how complexity can enter into all sorts of regions of analysis. So let's do a few examples now. From convex functions, this is more details of convexity. Each of the ax is convex. X is p is convex, so p bigger than 1. Minus of x is convex, I put it in red for a reason. And x on x convex on these two on the positive numbers. X to the a is convex, but only in certain regions of a. So a bigger than 1 or a interior is convex, otherwise it's not. Okay. So here's a very curious thing. I've shown you a function that's actually not convex over the whole line. I say x to the a over the whole line. It's still a convex function, it's still a concave function. In some places it's convex, in other places it's concave. But now let's look at the log of this. Well, then it is convex. Actually, negative log is convex on the alpha plus. So if I imagine x positive now, even if by x to the 1/3, I've turned a function which is sort of ill-behaved, not convex or concave, to something that is convex. And that means, suppose I want to maximize x to the 1/3, such as the space. That's the same as maximizing log x to the 1/3. I've got a free lunch almost. I've changed the problem that's not convex as well as this one. So people take large sources of reason. Here's a pretty good one. So the convex functions, these are all convex functions on R or subsets of R. How about Rn? Here's a convex function. This just makes the point that convex functions do not have to be smooth, they don't have to be differentiable, they don't have to be this is not smooth or differentiable. This is also a convex function. It's actually an approximation to the maximum, because whichever of these is the biggest gets pulled out. So x2 is much bigger than the rest. This one this is just x2. The negative geometric mean is also a convex function. And it's also defined on our class. So here's the sort of machine learning one. This is logistic regression. This is what we're talking about logistic regression. The probability of xi, the parameters z alpha I, are just modeled this way. Okay, it's like softmax logistic regression. So if xi is skewed, the probability is, if alpha is skewed, the probability is large, and so forth. So this is a puzzle, it's in green, so it's a puzzle. Show that this is not a convex function, and it's not a concave function. But its negative log is convex. So it's not a magical thing. And hence, it's very easy if you just use this identity, that a variance is always bigger than square root. have a convexity under our belts. Let's prove it happens with the quantities that the other lecturers have been using and will use, continue to use. The multi-version, by the way, this inequality, so in some cases it's just an inequality, but it's just a definition of convexity. There's a multi-lambda version of this thing. Okay? It's just got one lambda, right? Between 0 and 1. That's the definition of convexity, and between 0 and 1. Now, so we've got a bunch of lambdas, it's like 1 and positive. Then if f is convex, it's all puzzle for you, shows that this is also true. Sort of multi-lambda version of the convexity definition. Now we can use that to prove that the geometric mean is always less than the arithmetic mean. Let's do that. So we're going to use the fact that negative log x is a convex function. Okay? Here is the arithmetic mean. So I'm going to choose my lambdas. Each lambda is going to be 1 over n. So now this is a combination of the x's. So this is the negative log of this. If this log is convex, this is true. Okay? And then just expanding out this, it's the same as the log of the products, right? And so there's my inequality, turning that around, I get this here. It's only true for xi positive, as this is prime. But this shows you the geometric mean in n dimensions. It's always less than, it's always bounded up by the arithmetic mean. So now we have this, we can pretty much in one line withhold this inequality, which is used in various places. And this is withhold this inequality. You've got a p and a q, p is bigger than 1, and one of the people in front of the q is 1. Remember, this sort of ends in p norms. Here it is again. So just the regular old dot product is bounded above by take up to valuation of p, which is 1 over p, and the same with q. How do you prove that? We're going to choose lambda as 1 over p and use what we just proved, geometric, with an arbitrary lambda actually. You can also prove this, exactly the same way we proved this. So we're using this inequality. I'm going to choose a special version of A, a special version of B, stick these two in here, and you get this random. So convexity is powerful. You can prove seemingly complicated theorems that we use sometimes using convexity. Since we're on the subject, let's just prove the other one that always goes with whole inequality. That's the constant inequality. So for p greater than 1, the constant inequality says this. And it's like the kind of inequality for the option norm. Right, so okay. Or equals to this kind of inequality, p equal 1. For p equal to 1, you can just use the ordinary kind inequality. For p bigger than 1, there's some q such this is true. Okay, so let's just prove this. So this, just take one of these out to the side, that's something for this. Then use, okay, this is, let's make this from whole inequality. This is whole inequality here. And then I'm just going to use this fact to get this, divide by this both sides, and get that thing. Let's do that on the printer, but I'm not yet. So you can check this if it's correct. Okay. On to the main subject now. What is convex optimization? By convex optimization, people mean the act of minimizing a convex function over a convex set across the screen. So you've got a set of points over which your function is defined as convex. The function itself is convex. Minimize that, that's a convex optimization problem. And remember that if f is convex, then f negative, or f less than some number, the function is a convex set. All the x's are identified as 4 convex set. And that's just a one-line proof of this. So we're also going to use the fact that the intersection of two convex sets is always convex. Okay? Now given these two things, you can also rewrite this in a slightly more mathematical form. Convex optimization problem is minimize some function subject to a bunch of some convex function, subject to a bunch of other convex functions being negative or 0 for all I. And what's happening here is, because these are all constraints, they all have to hold, and that means that each set defined by those x's that satisfy this constraint, when I require that they all hold, that's the intersection of those sets, right? But that's also convex, so that means I'm minimizing a convex function over a convex set, so I have a convex optimization. So here's a really useful fact about convex optimization. All solutions are global, and the set of global solutions is convex. What do I mean by global? I mean, if you've got two solutions, the value of f in two places is the same. So there is a global value of f. what is the solution to this. So maybe some points that give that value of that, but it's always the same number. And the set of normal solutions being convex means if I just take the x's that give me these normal solutions, and I look at that as a set of points, that set of points is also itself convex. And the proof for this is very easy, so let's just do it to show you. So suppose S is the set of solutions, and that's the optimal. And suppose it's local, and it's not global. Then there's some x that's lower, right? By assumption. Gives you a lower f. That's also in this convex set. Form the line joining these 2 points. By the way, this is used again and again in proofs using convexity, the convex analysis, etc. Then this, by the convexity, is less than this, which is certainly less than this, because this is less than this. So I can x star here and get things are equal, so an f vector is less than x star. Now I take the limit as I go to 0. That means that I found something that's less than x. Right? So this can't be true. So it must be that all local solutions are in fact global solutions. Okay, the next part, which is that the set of global solutions is itself convex. Suppose you've got 2 solutions now. Again, form the line joining them. Then f, along that line, because that is a convex itself, is less equal to this. But we know these solutions f is the same value. So therefore, this is true, right? Because f of x0 equals f of x1. And so all of these points lie in a convex set, if this is true. Okay. Here's a little uniqueness here. We just want to throw this in to show how this is used. How powerful this can be. Okay, suppose you've got some vector in Rk in a set of variables. Some set of variables you're optimizing over in your machine learning problem. And there's some other set of variables you're also optimizing over. You've got 2 sets of variables, and then there's a real value strictly convex function defined on the y's, and just a convex function, not strictly convex necessarily, defined on the x's. And let z be just the union of these sets of variables. So I actually haven't said this, but the x's can also share the y's. Some of these variables can be in common, okay? And now suppose you're trying to solve this problem, convex optimization problem, where n is not one of the variables necessarily a plus b, because some of them could be shared. And you've got some optimization problem like this. It's a sum of a strictly convex function, and then a function that's not strictly convex, and some of these variables may or may not be independent. And this happens a lot. People write down these kinds of things. And all solutions to this problem have the same value of y. They're unique in those y's for which this is strictly convex. So, a corollary of this is that the W that you see in SVM machines, Duality machines, and new Duality machines, for classification and for regression estimation, there's a bunch of algorithms there. This is the W that tells you the width of the regression tube, the regression, or the direction of the separating pattern plane for SVMs. It's always unique for any solution to an SVM problem. So we kind of stuck on minimize something subject to a bunch of convex constraints, but we want to maximize something or change the constraints to being concave or something like that. What goes wrong? So let's just think about why are we sticking in minimize? What if you try to maximize the convex function of the convex constraint? So let's just try it. This convex function, the constraints are convex, there's only x is on the line, it's a semi-convex set here. And we're maximizing. Well, there's 2 points. There's one here, there's one here. So now I've got local maxima, which we kind of ugly. Same thing happens if you minimize the concave function. So if you turn this upside down, it's now concave. I minimize it, I've got exactly the same picture, it's upside down. It's the same problem first. All right, well, suppose we stick with minimizing a convex function. But suppose it's over a set of itself not convex. So now I'm going to split my x's up. I'm going to be minimizing over these x's. It's not convex because I can try and correct the line here that doesn't lie on the set. Then again, you get local solutions. This is the solution and this is the solution. Minimize again. And by the way, I'm making another point here too. F itself is in fact not convex because it bends around, but it doesn't matter. It only has to be convex over the sets that you're optimizing for this to be true. Something that's worth remembering with a convex optimization. It doesn't matter that this bends down because you only care about F here and here. But this is not convex optimization problem. So stay on the top. You want to minimize convex functions subject to convex constraints. All right, some simple examples. for any unconstrained optimization problem, just minimize that, then it's actually very simple. The gradient has to vanish. Why is that necessary and sufficient? Well, if f is convex, it's testing for positive definite. That means that if you find a point where this is true, there must be a minimum. Right? It's the testing for positive definite. Let's look at a slightly more an example of that. I want to minimize this guy, just in general. Okay, so I find the gradient after the vanishes. That gives me this, and back with SVD. Now I get the complete of a solution to SVD. And what does SVD gives me complete of solutions to a linear system like this. Norms, people use norms a lot, because they're convex. You could have a norm appear in an objective function that's just like this, minimize some machine learning norm, and it could also appear in constraints as another norm, convex function less than a constant. So this is also kind of useful. Okay, so let's do some examples. We're going to get to duality and also to stuff in it, but just some quick examples. Minimize this. This is a linear programming, subject to sort of constraints. This is mine. So if A has rank K, then it has an SVD, minimum SVD condition like this, remember? And it also has generalized walk and row reverse, like this. So clearly, if B is not in the range of A, there's no X that satisfies this. So it's infeasible, it's a solution. Otherwise, it has to be of this form. Whatever the value is takes, it has to be accessible like this. So generalized inverse times B plus something in the null space, where the alphas you get to choose, and the E's scan the null space. Okay? So now, if the inner product of C with the null space of A is not 0, then you can always choose X as large as you like. You can choose X along the null space, but so that this doesn't vanish, you make it bigger if you like, so it's no solution. Right? Otherwise, this is the solution. And it doesn't actually spell it explicitly on C, it's just an implicit thing of where the problem is set up. Okay. Here's a very simple one, and let's just demonstrate how changing the problem a little bit is much harder. There's a whole art to linear programming. It's not easy to survive with linear programming. But it's a simple solution. Simple problem. So I'm going to minimize this again. Convex if it's linear. Subject to box constraints. Every component of X has to lie between lower and upper. Okay? Well, that's pretty easy. Just by inspection say, well, okay, if a component of C is positive, then make that as small as possible. If a component of C is negative, it doesn't matter what you take it as. If it's negative, make it as large as possible. So this should minimize this for Z, with one step. Now suppose I make it slightly different. We're going to go to a quadratic programming problem instead of a linear one. Still got box constraints. I'm going to add, say, this constraint over C some vector. Anybody recognize this? This is the problem you can solve to compute spot vector. I mean, this whole paper is written on how to solve this, right? This is the dual problem of solving the spot vector classification problem. So it's not easy, as this is. So don't be surprised if by changing one thing, the problem gets much harder. Okay, let's do another one interesting example of a linear program. That's something called the Chebyshev center. And that's this, you can imagine, want to define the largest ball that fits inside some polyhedron. Polyhedron is defined by a bunch of planes. Actually, polyhedron doesn't have to be closed. It's closed, it's called a polycone. So the center is the furthest internal point from this boundary, right? You want to find that. How do we do that? So polyhedron is defined by those x's and off the end. Such as the line on the right side of the hyperplane, this is the hyperplane here. And the ball is just got some center plus some thing that a vector that is slightly inserted to the ball. So this vector is size r. We're going to maximize this radius r, subject to the ball being the size of this polygon. So B must lie in this half space, right? Because these are constraints. And that's true if this is the case. Just plug an X, which finds this sweeps out the ball. So this will be true. And that's certainly true if it must be true that U is, this will be true for all U inside the ball. You can find this ball. Now, the biggest value that this guy can take is just R times the size of this vector. Right? So this constraint becomes this. Use this here, I made our the worst possible case, and I require this picture. It's kind of nice. This is what I'm operating over. These are just constants. These are just constants. I'm operating over this too. So it boils down to this problem. Maximize the radius, subject to these constraints. And now it's a linear programming problem. So you've got a problem that looks like it might be horrible. I mean, spheres, turns out it's linear. But again, well, puzzles first. I slip something value. I'm maximizing R, not minimizing it. Something should have thrown straight at me. Why is it okay to do that? I'll just give you an example of why it's not okay to do that, and now you say it is okay. How about if you ask for the minimum sphere enclosing a pointer? Is that an LP too? How about the minimum enclosing sphere for some points? It sounds very similar. Actually, it's not. It's probably. Just to go one step further in this direction, what about the maximum size ellipsoid that fits inside a point? Now it really does have to be a pointer for the product ether. Otherwise, we could have the ellipsoid is leak out of this thing, it wasn't closed, right? So it has to be a closed pointer. If you class this problem as follows, the ellipsoid is this set here. So right from the ellipsoid is this. Any vector in Rn, that's the center. This describes a squish this, just like a Gaussian array. We want to minimize the volume of the actually maximize the volume, which is to minimize the negative volume, which is a convex function of the pointer, looking at this ellipsoid, subject to the constraints of the right side. And it turns out you can write it this way. So E is the matrix, these are the constraint vectors of the final pointer, and it's very nice. But it is now a much harder problem to do the constraint here. And this E is always positive definite. And E is what we solve before. Right? So it's a different layer 2 problem. Okay, let's talk about duality. What is duality? By the way, some people ask whether these notes that we made available are not quite the same as the notes in your notes. They will be. I'll give you the most recent ones. I'll make 2 per page so you can actually read them too. So now, suppose you've got a general. Now, I'm not talking about convex problems at all, just general problems. General optimization problems. Minimize some function, subject to a bunch of constraints. Inequality constraints, another bunch of equality constraints, appear those types. And they all take X in Rn and map it to some number. All these functions do that. That's a very general optimization problem. Not enough to do that. So look back in the first section, we talked about how to impose constraints by increasing the function, each constraint and determinable around multiplier. And for inequality constraints like this, where this is negative, by minimizing, these have to be positive, otherwise they are unconstrained. And for the inequality constraints, the ground multipliers are unconstrained. So solving this problem has this Lagrangian, which okay. Now we're going to find another completely different, well, a related function called the Lagrange dual function, which is a function just to the Lagrange multiplier. And I'm mapping now some function n plus p numbers, right? And it's the infimum over x in the domain. The domain of this problem is the domain of f intersect the domain of c intersect the domain of. It's the inf of this guy. That's the Lagrange dual. It's another function that's associated with this problem. So now here it is again. Lagrange dual is written out again. And clearly, because this is an infimum, this is always for any feasible x. This is 0, right? Because it's feasible. And these are negative. And this is an infimum, so that means that g must be less than f of x. In particular, g must be less than the max value of f, the optimal value of f. So this g is always below your f. And then some, okay. So you might say, okay, here's a different way to solve the same problem. I'm not going to minimize f, I'm going to maximize g. Maybe I'll bump into this f that I need. That's what I'm looking for. By lowercase, lower star, I mean optimal value in these terms. So let g star xi would be the maximum of this Lagrange dual function, then this is definitely positive, which it is. And in fact, the difference is we think it's called duality gap, the optimal duality gap. So now we've got a different problem. Just from noticing that it's always true and maximize this to solve the problem, maximize this such this. Okay, this is something very interesting. This is a convex optimization problem, even though this need not have been. So now it turns something into a convex optimization problem. If these two are equal, if they actually bump into each other, then strong duality follows. This means the duality gap is zero, it vanishes. It doesn't always hold, even for convex optimization problems. There are convex optimization problems for which this is not true. And there are non-convex problems for which it is true. So it's, you have to just check. However, there are tests you can do to see if your problem, strong duality holds or not. Let's do an example to try and gel this stuff. Very simple example. We're going to minimize the function. This whole thing. So these constraints. Okay, let's write down. You can see right just by looking at it what the answer is. Feasible set has to be between 1 and 3. This is negative. The optimal solution, well, we're minimizing this, so x is not responsible. Optimal solution is 1. F, what's the value of f? X is 1. It's 3. The Lagrangian I get just by saying f minus 9 is the constraint plus the is this. Lagrange dual is the info to x of the Lagrangian. So it's different with respect to x, substitute that's the Lagrange dual. And the dual problem is to maximize this guy, so these being positive, convex problem. So taking the derivatives, you get two solutions. So this one's not feasible, because it's actually positive. So at the solution, lambda is 1. On g of 1 is 3. And f is 3 at the solution. So here's a case where strong duality holds. Just to do this in pictures. Okay. When my objective function is x squared plus 2, that's the same as the Lagrangian with the Lagrange multiplier set to 0. So the blue here is that objective function. The feasible region is everything between 1 and 3, and the other side is infinite. So now I'm going to plot the Lagrange function for a couple of different values of lambda. Lambda is 0.5, and lambda is 2. This one, 0.5, 2. Remember the definition of G, it's the minimum over x of L. So I'm looking for a minimum. So that's this minimum here between one of my g values, this minimum here between another of my g values. So for lambda is 2, minimum is 2 and 2/3. Lambda is 0.5, minimum is 2 and 5/6. And notice that I'm outside the feasible region here. This minimum is not over surface domain, it's over the feasible region. It's still true. Okay? That this is always known as wherever you look. In fact, you can plot G as a function of lambda, here it is. And it also holds its maximum value is 3, which is the minimum value of f. My objective value. There it is, 3. Everywhere else, it's lower. Okay, so this is sort of picture of how this works. Just a little puzzle for you. Why do all these terms show these 2 points? For this particular problem. Okay, let's do some examples. So minimize the square of x subject to equality constraints. Okay? Here's my Lagrangian. And okay, so x means this. And I have to find the info to the L, then my dual function. It's just this. Okay? So I set the gradient of f, I just find the influence over of L over x. What that in here? Get my dual function. For all LPs, the dual is also a linear programming problem. And for linear programming problems, it's a very special thing. Strong duality fails only if both of these guys are reducible. If one of these is reducible, the other is not. The other is equal. It's still not strong duality. And for linear programs, the dual of the dual is equivalent to the primal. In general, that's not true. So here's another example. It's now a combinatoric problem. Okay? I'm going to minimize this subject to each component squared must be 1. Well, that must mean that xi is plus or minus 1. So to find the solution, you just plug it in across the value of x having plus minus 1. If you've got 1,000 of these, you've got 2 to 1,000 things to check. This gets rather unpleasant at this combinatorically high. So the dual now, just going through the steps, is exactly this. It's the value of minus infinity outside the equation, and it's minus the 1 vector dotted into these views. The amount multiplies these constraints for any for which this is true. Okay, positive and definite. But that means that because I know that the dual is a lower bound for the solution, I can pick any value for the dual and know the solution must be above that. That means I can get a lower bound for the solution, right? So here's a lower bound. This is dual feasible. This is the smallest eigenvalue of A. That times the 1 vector plugged into here gives me a value of G, which I know is a lower bound on the solution I'm looking for. And there it is. So we know whatever the solution is, it could be very hard to get. In fact, this is very hard. We do at least have a lower bound. And this is the 1 plus the 1 is the n. So this is just the same number, all down this vector. So my dotted with 1s over here, n times the minimum eigenvalue of A. It's simple. There's no way duals are used, not to solve problems, but to bound them. I need a couple more definitions before this really general stuff. So we talked about norms a lot. What about a dual norm? It's another meaning of the word dual. The dual norm is a prime. Now the upper star means dual, and the lower star means optimal value of these terms. Okay? You take your norm, you look at the sphere, you find out the norm, and you find the u, which this is maximized. Then that is by definition the dual norm of this norm. In fact, in order to define a dual norm, you only need a pre-norm, which is the norm without the triangle topology. Okay, in that case, this dual norm is the norm. It is an interesting thing about dual norms. You've got some vector norms, some pre-norms, okay? Then the dual norm is that, so suppose that's the dual norm, and choose some positive number. When is a norm proportional to its dual? For all x? The answer is it has to be the Tübingen norm, only the Tübingen. And another way to see how these dual norms enter into the P norm idea is that for any positive P given 1, the dual norm and the regular norm will relate this way. The dual of the LP norm is the LP norm. So that's dual norm. It's a bit tricky because it's not always obvious how to compute this, right? But nevertheless, it's useful to write it that way. A similar thing you can do with functions. So now I'm going to find something called a conjugate function. Conjugate of a function, very similar. Take my function, subtract it from some y dot x, and I look for the max of that. I look at the domain of that. Again, it might be pretty hard to compute, but you can compute it in various cases. The domain of the conjugate is defined to be those y's for which this is the primary object. And interestingly, just as the dual is a convex optimization problem, the dual function is convex whether or not this function is convex. You can see that might be interesting. Certain properties of convex one. Let's go to 2 examples. Here's a linear function, the affine function. The domain is just, the domain of the dual is just a single point, otherwise it's infinite. And the dual function at that point is 2. For minus log x, the domain is negative numbers, the domain of the dual, and it's also just a log. E to the x, the entire positive line is the domain of the dual, and this is what it is. And finally, x log x, the entire line is the domain of the dual, and that's the dual function. So why are these interesting? Okay, define these strange functions. I think I'll speed up. Is that okay? We started 5 minutes late. I've got 5 minutes left. I'll just keep going. Two examples in Rn of these are constant functions. I'm just giving you examples in R. Here's 2 examples in Rn. This function doesn't necessarily well, a norm is a tricky one. If f is just a norm, the domain of the dual is a column space, and this is the dual, conjugate function. This is the conjugate function. 0, if the dual norm is less than 1, then and it's infinite otherwise. And this you can pick up as an indicator function. Wherever it's 0, that's where I want to go. So the conjugate of a norm, that's what this is the indicator function of the dual norm. That's what this is. Dual norm. So now that we've got dual norms and conjugate functions, we can write down very general solutions. Minimize this, okay, and I'm still with the details in terms of answers. So first, minimize the same as introducing quite many variables, minimize that subject to constraints, and the dual function, the dual Lagrange function, can be written in terms of the dual conjugate function. So here, I haven't said what f is, and yet I've been able to write down the dual function, because I've got this idea of conjugate function. So for example, you should check this. This is all now green, okay? Minimize some object, this affine function x for any norm, and this gives the dual problem maximizing the view. It's this, subject to the dual norm less than 1, with these constraints. So again, it's very similar. I haven't said what this norm is, but if you know what the dual norm is, then you can get the dual Lagrange functions for optimized groups. Similarly, minimize this such these gives you can write that in closed form. As long as you know what the conjugate is, if it's f and any f, that is the Lagrange dual. One very important point about the Lagrange dual is, suppose you've got a primal feasible x and a dual feasible y with this, so these to satisfy the constraints. Then we simply know that a strong duality holds. F of x lies above the optimal, and g lies below f. And that means the difference between your value of g and your value of f, somewhere in that gap is the solution. And if that gap is different from -16, the chances are you're going to numerical to stop your algorithm. Right? So you can use the duality gap as a stopping criterion for an optimization. Here's an example of a non-convex optimization problem that has strong duality still. It's nasty because this is not convex, right? It's not a convex set. It's around the sphere. Here's a very interesting thing. The dual, this is the dual. This is the solution to the dual. How do I define a dual function? I take my Lagrangian, I take my integral limit of my x's over the domain, and then I maximize that. That's what this guy is. It turns out that the final problem can be passed this way. Clearly the sum over lambda first is equivalent to just concentrating on those points for which the constraints hold. And then finally again is finding the solution. So this is always true. If this is an equality, then the zero duality gap. Right? In fact, this is true for any function. It's an exercise. So you've got some function, two sets, and you swap these supplement dips. Then this inequality is always true. This little exercise is true. Just choose 2 points each. Find a function which is an extreme inequality. Okay. I have 2 more slides, I think. Good. Complementary satisfaction. Now, again, I'm not assuming complexity here, assuming the strong duality. Then the solution is equal to the solution to the dual problem. This is the duality gap. That's equal to this. By definition, that's equal to this. Right? And since these are positive and these are negative, this is less than or equal to, and this is an interval, this is less than or equal to this. That's an interval. Well, I've bounded something. These are negative, or 0. These are 0. Right? And these are 0 because they're quantum constraints. These can at most be 0, otherwise they're negative. But they have to be negative. They have to be 0, otherwise it's an inequality can hold. And that means that this is the solution. And that means, since all of these are negative, each of these must be 0. And that's a complementary space. And a okay. So for any problem which strong duality holds, whether or not it's complex, at the solution, these conditions hold. So now, this gives us the Grushin quantum conditions. So for complex strong duality, we have an opposite complexity, 0 duality gap at the optimum. These two, the minimum of the primal and the maximum of the dual are the same. And that's equal to f over x by definition of g at the solution. And that's equal to this. Okay? Now, if these are all differentiable, then I can differentiate this and get And these three things together are what define KKT conditions. Usually people say KKT is symmetrical this, but in fact it's everything. Okay? First of all, the constraints have to be met. That's certainly true. Secondly, complementary slackness holds. I'll show you that. And thirdly, is gradient management. Just a regular gradient management decision. Now, what's interesting about KKT conditions is, for any optimization problem, the primary and dual optimal points must satisfy KKT. Okay? And secondly, for any complex optimization problem, if the points satisfy KKT, then they are the solution. They are primary and dual optimal with zero duality gap. That means that you can solve optimization problems by finding things that satisfy the KKT conditions without doing anything else. Sometimes it's much easier than just sometimes you just try to solve the KKT conditions. Quick example, and I'll stop. Minimize this quadratic optimization problem subject to the quantum constraints, H is constant definite. This one is Gaussian. What are my KKT conditions? Well, remember I have to have constraints as well as constraints, and also the gradient mansions. Of course, there's no inequality constraints in this problem, so that disappears. H dot turns it out. Now I'm just claiming, because this is convex, I can find something that satisfies these two things, I've solved the problem. But that's easy. It's a linear system. Okay? Here it is written out as a linear system. These are the solutions. So now I've just solved with SVD again. Here's the with SVD again. You can see why SVD is important. Okay, that's it. Thank you very much.